Okay, in this screencast, we're going to look at three different circuits. They represent each one of the big three: parallel, series, or combination. We're going to figure out how to analyze the circuit and go through that specific process and give you as much information as we can along the way. Okay, so first, we're looking at circuit number one. First thing to always do is identify what type of circuit it is. Now, the negative terminal is here, the positive terminal is here. Everything attached to this positive terminal has low potential. Everything attached to this negative terminal has high potential. And the current is going to flow out of the negative, down across from high to low potential, and back into the battery. Because all three are connected between the same points of high and low potential, this would be a parallel circuit. Okay, now we know in parallel the potential difference is all the same. We know from here that the total potential difference at the battery is 60 volts. Therefore, delta V1 is 60 volts. Delta V2, change in potential difference, is 60 volts. And 60 volts, they're all the same. Okay, now we know their resistance values. So this first one is 15. From that, we can always determine the individual currents, because we know that I is equal to V delta V over R for any given resistor. So V1 is 60, R1 is 15, 60 divided by 15 is 4 amps. V2 is 10, 60 divided by 10 is 6 amps. And then R3, delta V3 is 60 volts, potential difference there, and 20 is the resistance, so that's 3 amps. Now to get the total, we can just add up those other three. 4 plus 6 is 10, plus 3 is 13 amps. And then we can go ahead and solve for the total resistance. Again, R is defined as the delta V over the current. So we have 60 divided by 13 would give us 4.6 ohms. Okay, now it had to be smaller than 10, and it is, so that's a good sign. If we add up 4, 6, and 3, we have to get 13. Well, that's how we figured out the 13, so we know that's correct. And then again, it's parallel, so they all have exactly the same potential difference. Now, we could have used the idea of a parallel circuit in the first place and found the 4.6 by doing 1 over 15, so 15 x to the minus 1, plus 1 over 10, so 10 x to the minus 1, plus 1 over 20, so 20 x to the minus 1, equals, now that's the inverse of the resistance, so x to the minus 1, one last step, and we get 4.6. So we could have done it that way and then broken down the currents in the opposite direction. So there's more than one way to get to this, but it works approximately the same way. It's just up to you which way you want to go about it. All right, next circuit. Now this time, if we leave the negative terminal of the battery where we have the high potential and come back to the positive where we have the zero or low potential, there is only one direction for the current to travel. One path. One path is the sign of a series combination. Okay, in a series circuit, we just add all the resistances together to get the total. So 15 plus 10 is 25, plus 10 more is 45. And then I is equal to delta V over R, so it's going to be 60 divided by 45. Now you should notice that we took the exact same resistors and we got a much lower current. Much lower, about 10 times less. Again, in series, because there's only one path, the resistances will add up and your currents will be very low, will tend to be very low. In parallel, because of the increasing of the pathways, the current will tend to be very high. And because it's series, I don't do any need to do any more work. I can automatically say that the current everywhere is exactly the same. There's only one path. Charge is current. Current is charge. Charge is conserved. So therefore it must be the same everywhere. Now when I do delta V1, delta V2, and delta V3, when I calculate those and add them together, I need to come back to 60. Again, delta V is just going to be I times R. So it's going to be 1.3 times 15, 19 and a half, and that's volts. And then 10 times 1.3 is 13 volts. And then 1.3 times 20, which is going to be 26 volts. Add those together as a quick check. 26 plus 13 plus 19.5 should come out to 58.5. That's close enough. We could have rounded this a little more and gotten closer to 60, but that's close enough. We are definitely on the right path. So that's it for that circuit. That's all it takes for a series circuit. Now, a series circuit's pretty simple, so that's why whenever we have the following type of circuit, we usually get rid of the parallel first and then solve it as a big series circuit. So here we have a section where this side over here is attached to the positive terminal, and this side over here is attached to the negative side. They're both attached to the same, across the same positive and negative, so they're both in parallel. So these guys are in parallel with each other, and then this one's all by itself. That's going to be in series with the other two. So this is a combination circuit. The first thing I'm going to do is figure out what is the overall resistance of this group, and then essentially I'm going to redraw the circuit to have just one resistor where the two were before, and that's by doing that I'll turn it into a series circuit. So R1 and R2 are in this case 47 and 33. So 47 x to the minus 1, let's clear that, 47 x to the minus 1 plus 33 x to the minus 1 equals, and then x to the minus 1 equals 19.4. Okay, so those two are worth 19.4. So it's the same as having a 19.4 ohm resistor here and then the 68 ohm resistor here. So we say this circuit is equivalent to the same as this one up here. Now it's a series circuit, so to get the total resistance of this one, I'm just going to sum up the other two, just add them together. So 19.4 plus 68, and we're at 87.4, and that's ohms. The input source voltage is 120 volts, so again I is delta V over R, so we're talking totals here, so 120 divided by 87.4, and we're looking at 1.37. Okay, now I made this equivalent to a series circuit, but it's not truly equivalent, so I can't just say that this is going to get 1.3, each of these is going to get 1.37. I know that they have to add up to 1.37, but they're not going to get that exactly that same amount. So now I'm going to want to go back over to my original circuit and revisit to get the rest. So this one's all by itself, so it's going to get the total current, so R3 is going to get 1.37. It has a resistance of 68, so I is delta V is I times R. So I can take 1.37 and multiply that by 68, which is its resistance. It's going to use up 93.2 volts. Okay, so it's the biggest part. It's going to use up the biggest amount of the potential difference. Okay, now the other two, they're going to split, but unlike our first page here where we worked on the other side in part A, they're not going to split equally because they're not the same amounts. I can, though, figure out how much their voltage drop is going to be. It's going to be equal to each other, and I can figure that out by tracing around one loop of the circuit. Now I'm putting in 120 volts. I have to use up 120 volts. I'm losing 93.2 volts in this one. So that means the potential difference of R2 has to be the difference between those two. So 120 minus 93.2 is 26.8. And then this has to be the same as that because those two are in parallel with each other. Now we can go ahead and solve for the individual currents. Again, I is equal to delta V divided by R. So 26.8 divided by the resistor value for R1 is 47, gives us 0.57 amps. And then VI2 is going to be the same potential difference, 26.8, divided by its resistance, which is 33, and that's 0.81 amps. Now we can do a quick check. If we add these two together, hopefully they'll be right around 1.37. So 0.81 plus 0.81 plus 0.57 gives us 1.38. Close enough. Okay, so that looks good. That's it. We've got everything about our circuit. And figured out all the currents, all the individual pieces of the puzzle. The last step we'd probably want to start looking at is what's the power rating of the circuit, and we could do any of the power relationships now to figure that out. We could take the potential difference times the current, multiply those two together. We could take I squared times R, or V squared divided by R, and figure out the power of each individual piece of the circuit or the circuit as a whole, and then get some idea of how much energy it transfers. Okay, so that's how to analyze the three basic types of circuits that you have to deal with: parallel, series, and combination.